All right, here we go. So let us talk about rate of change. And this is a calculus concept, and it's directly related to derivatives, as I've been talking about recently. All right, so first of all, let's kind of build into this. So you might recall when you've learned about um, I guess rate of change perhaps in the past. If you have a change in the x value, like let's say you go from x1 to x2, then you would say the change in x, which is known as delta x, is going to be equal to x2 minus x1. So that's literally how x changes when you go from x1 to x2. That's delta x. The change in y, or keep in mind that y is equal to f of x. So the change in y is going to be equal to f of x2 minus f of x1. So basically, as x changes this way, y, remember, y is a function of x. So that's why you have y when x is x2 minus y when x is x1. That's essentially what you have here. So then you have um, delta y over delta x, which is known as the difference quotient. The quotient of the difference between the y values and the x values. That's going to be equal to, just plug this stuff in. So f of x2 minus f of x1 over x2 minus x1. All right. Now, this is known as the average rate of change. Okay. Now, if you recall, the derivative gives us what's called the instantaneous um, rate of change. So what happens is basically the way you look at it is as delta x, as delta x goes to zero. So watch this. Okay. So as delta x goes to zero, so in other words, as you, and you really probably need a visual here, but try to imagine it for the sake of this video. So if you think about it as, because this average rate of change is going to be, so let me do it this way. I'm going to do a very simple drawing because it's better to illustrate this. And let me see. I'll do some different colors here. So if you have some line that looks like this, and you're trying to find the slope. So say this is what you call x. What's this? This would be x2. This would be x1. Okay. Now, and what you want to do is, and so if this is the coordinate for this is literally going to be x2 and then f of x2, and then this is x1 and f of x1, right? So basically, when you find the average rate of change, that's delta y over delta x. So here's your delta y. So I should have probably not drawn those there, but it's okay. So this right here is your delta y. How y changes when you go from here to here, right? This right here is your delta x. So it's how x changes when you go from x2 to x1. Okay. Now, so what happens is y over x ends up giving you your slope. Your average, it's like, let me put it this way. It's like the slope of a secant line. So this line right here is your y over x. Okay. Now, as now let's go to this concept here, which is where the derivative comes from. as delta x goes to 0, in other words, as the difference between these goes to 0, what happens is you're getting closer and closer. They're getting closer and closer together until there's really like no difference. So that means as delta x is going to 0, the limit of, and let me write this here, of this of delta y over delta x is what's known as your dy dx. That's your derivative, also known as the instantaneous rate of change. Instantaneous rate of change. In other words, what that means is, sorry about that sloppiness. That's like the change in an instant of time where you find the slope at a certain point. That's really what this illustrates. Okay. That's where the derivative comes into mind. All right. So let's see. Now, building on that, we can use the derivative to find the rate of change for different applications. And when I say different applications, I mean like different sciences. I'm going to use physics for an example. So hopefully this is kind of giving you like a refresher here. All right, so let's do this. Let's go ahead and clear all this stuff off. Let me see if I can. Okay, so let me kind of do some erasures here. Kind of clear the way for rate of change as it pertains to physics. Now this is some of the stuff that really makes calculus cool, because and I illustrate it here in a second. Let me not get ahead of myself. All right, so this is as it pertains to physics. All right. So say you have some function s and it's equal to f of t. This is what is known as your position function. Okay? And so literally we're talking about the position of a particle. Just some particle, some random particle in space. And we're talking about the position of this thing as it moves in a straight line, okay? It's moving in a straight line. All right. So now, if we were to take what you would call the change in S over the change in time, so you have a particle that is moving along this line, and we're wanting to know how is it moving along the line, like as far as like its rate. So how is it moving with respect to how is it changing with respect to time? That's what S delta S over delta T is. So that's literally the we're talking about velocity here. When you're talking about a particle moving with respect to time, that is velocity. You know, like miles per hour. That's basically what it is. So this is what you would call your average velocity. It's your average rate of change, basically. Now, if we want to find the instantaneous velocity, basically what we're going to do is we're going to do, okay, so we're going to take the derivative of this. So it's going to be S prime of t is going to be the instantaneous velocity. Like I said, this is where it's cool because what happens is, whereas you might be used to finding velocity kind of in this manner, like with algebra kind of stuff, this is going to give you a better measurement of what velocity is at a particular point in time. This is like an average velocity over like a span of time, going 50 miles over 2 hours. What was the average speed? But this right here will help you to know how fast was the person going at this point in time. So say you have a function like so. Actually, I better go ahead and erase. Oops, that's not what I meant to do. I meant to do an eraser. So let's Try that again. All right. So say that we have a position function. You have s of t, or I say, how do I want to say this? I just be consistent with the way that they're saying it in my book here. So s is equal to f of t, and this function, this position function, is equal to t cubed minus 6t squared plus 9t. Okay. Now, we want to, for part A, we want to find the velocity at time t. All right. So what that means is, so we're wanting to find the velocity at time t. So since they didn't give a specific time, they just want us to essentially just find what the velocity would be at any time t. In other words, all we're going to do is find the velocity function. So v of t is going to be equal to f prime of t, right? Because when we take the derivative of the position function, it tells us the rate of change. Okay. And so that's going to be equal to, now you find the derivative. So use the was it the chain, the not the chain rule, but just find the derivative. So you got 3t squared minus 12t plus 9. So there you go. That's it. Now, the next part of this question asks us, what is the velocity at 2 seconds? And then what's the velocity? velocity at 4 seconds. All right. So literally all we need to do is at 2 seconds, t is equal to 2. So it's going to be v of 2 is going to be equal to 3 times 2 squared minus 12 times 2 plus 9. This is pretty straightforward to do with the on hand, by hand, I mean. 2 squared is 4, 4 times 3 is 12, minus 24 plus 9. So 12 minus 24 is negative 12 plus 9 is negative 3. Okay. So that's the velocity at 2 seconds. Okay. The velocity at 4 seconds is going to be equal to 3 times 4 squared minus 12 times 4 plus 9. So that's going to be equal to 4 squared is 16 times 3 is 48 minus 48 plus 9. So the velocity at 4 seconds is going to be equal to 9. So let me put the units in here. I meant to say um S is measured in meters. And then T is measured in seconds. So literally this is going to be 3 meters per second, 9 meters per second. Make sure you do your units. I'm pretty sure it was important in high school, but it's very important in college for certain. All right, so let's keep on going. So part C says, when is the particle at rest? Okay, so but this is getting pretty cool. So let's think about this. So look at this here. So this literally told us in part B that at 2 seconds, this thing was going negative 3 meters per second. So in other words, it looks like it was going positionally, negative velocity means it was going backwards. And then, but at 4 seconds, we're back to going forward, 9 meters per second, or the opposite direction, however you want to call it. All right, so now when is this particle at rest? So when is a particle that's moving at rest? It's at rest when the velocity is equal to 0, right? So literally, we want to set the velocity function equal to 0. So 3t squared minus 12t plus 9 is equal to 0. Okay. Now, if you look here, you can see that we can factor a 3 out of each of these terms. So it's like we can divide both sides by 3. So that becomes, so divide by 3, divide by 3. So t squared minus 4t plus 3 is equal to 0. Let's factor what times what is 3. That'll add or subtract to give you negative 4. So it's going to be t minus 3 times t minus 1 is equal to 0. So if we were to solve these, so when t is equal to 3 and when t is equal to 1, this is when the particle is at rest. So at these moments in time, this is when the particle is at rest. So you can literally kind of start to develop a picture of what this thing is doing. Okay. So let me think about this here. So look at this, just so you can kind of see what I mean. So if you notice here, so at 1 second, this thing is not moving. Then we said at 2 seconds, it's going backwards, negative 3 meters per second. Then at 3 seconds, it stops moving. At 4 seconds, it's actually going back forward at 9 meters per second. So you see, I don't have enough room to kind of draw it. Maybe I will come back another time, I don't know, and actually draw this example. But you can kind of visualize what's going on here. Losing space. Let me see. All right, so let's do part D. So pay attention to this part. So they ask us here, when is the particle moving forward? So let's ask ourselves, when is this thing moving forward? So we know in this case that the particle is going forward when the velocity is positive. In other words, when the velocity is greater than 0. So literally, we know that this is moving forward when 3t squared minus 12t plus 9 is greater than 0 when the velocity is positive. So basically, we know from here that this all factors down to t minus 3 and t minus 1 is greater than 0. All right, so let's think about this here. So we can't necessarily just say and solve for this and then be like t is greater than 3 and then t is greater than 1. So let's think about this. If we plug in 3 here, obviously this all goes to 0. If you plug in thinking greater than 0, if you plug in 4, 4 minus 3 is 1, 4 minus 1 is 3. And then what you see is for t greater than 3, then this is going to be true, because you kind of have to make sure you plug it into both of these and make sure it turns out right. So t greater than 3 is one of them, one of the solutions. And so what about when we plug in 1? When you plug in 1, 1 minus 1 is 0, so this all goes to 0. If you plugged in 2, 2 minus 1 is 1, but then 2 minus 3 is negative 1. So is negative 1 greater than 0? No. No, so you can't say that. You can't say that you can't necessarily say t is greater than 1, because that would include the value of 2, which can't be included. So you can say, what if you plug in less than 1? So if you put in 0, 0 minus 1 is negative 1, 0 minus 3 is negative 3, and then a negative times a negative will be positive. If you plug in negative 1, negative 1 minus 1 is negative 2, negative 1 minus 3 is negative 4, negative times negative is positive. So you can actually say, so for t is less than 1, this is true as well. Okay. I think another way you might be able to do it, you could say, I guess you could say, well, actually, no, you can. I was going to say that you could say t, all of t except for t is equal to 2, but no, if it's between, it appears that if it's between 1 and 3, then you can't do it. So, like, in other words, kind of like this here. Let me see if I can write this in one statement if it's possible. So t has to be greater than 1, but then, I mean, less than 1. But then, okay, so maybe you could say it like this. So t has to be greater than 3, but then less than 1. Okay, so that's kind of a weird way to write this, though. But yeah, t has to be greater than 3, but then t has to be less than 1. Technically, that's a way to write it, but it's kind of weird when you do it like descending order with the numbers like that. So anyhow, this is a way that rate of change can apply to physics. You can apply it to various other sciences and whatnot. For example, in my book here, they talk about um, chemistry, like specifically the rate of change of reaction of, I guess, of like molecules. Biology, the rate of change, the rate of growth of an animal population, and so on and so forth. You can really apply this in a lot of different ways. And what happens is it gives a better measurement of like the way something is changing than just doing like average change. If you follow what I'm saying. Hopefully this helps. If it does, make sure you like this video, share it with somebody, give me comments or whatever, and I appreciate it.